Okay, welcome to this presentation. Today we are discussing the solubility and the pH. Because if you check the solubility of many compounds, they depend strongly on the pH of the solution. That's why we are discussing the solubility and the pH. Starting with question number 27, because last time we ended the question 26. Question 27 is saying, by using example, differentiate the following terms: acidic oxide and hydroxide, basic oxide and hydroxide, and then amphoteric oxide and the hydroxide. So let's quickly see the answer. So we are starting with the acidic oxide and hydroxide. When you have the nonmetals, they react with oxygen to form the acidic compound. So there's oxide, so they are called acidic oxide. They are held by the covalent bond, and when they react in water, so they produce the acidic solution. So there's a compound are also soluble in aqueous base because, of course, they are acidic compound. When we be discussing the acidic oxide, so that means they are the compound which can react with water to produce the acidic solution, and also they are soluble in aqueous base. So these are the oxide of non-metallic element, so they are acidic oxide. For metals, oxide, so they are the basic oxide. But for non-metal, when they react with oxygen, they give the acidic compounds. They give acidic oxide, which react with water to produce the acidic solution, or they can also be soluble in the aqueous base. So as an example, if you have the sulfur trioxide, if it's reacting with water, then it will produce this acidic solution. Then if it is reacting with a base, it is also soluble in a base. That means it is a neutralization reaction, because this one behaves as a acidic, then plus, for example, if you are adding a base like sodium hydroxide, you produce this salt and the water, which means it is acting as a neutralization reaction. Let's see the metal. When metals react with oxygen, they give the basic compound. When they react with oxygen, the oxide or hydroxide that they are giving, they are the basic. Example is when you have the group 1, group 2, and also lanthanide oxide. This basic oxide, when they react with water, they produce a basic solution. And they also dissolve in aqueous acid. So that means the basic oxide are the oxide of metals, and when they react with water, they produce a basic solution, and they are also soluble in aqueous acid. Let's see an example. For example, when sodium oxide reacts with water, it is producing the basic solution. Then when magnesium oxide also, the group 1 and group 2, it is reacting with water to produce the basic solution. They can also react with acid to produce the salt. That means here they behave like base. Then with the active acid, there will be a neutralization reaction to produce salt and water. So normally, generally, the oxide of metal element are basic oxide. But we have an exception. There is an exception for metal with high oxidation state. We have also the oxide of metal, which can behave as the acidic oxide as an exception. But generally, the oxide of metals are a basic oxide. But with exception, metal with high oxidation state, they can also behave as the acidic oxide. An example is this one. So the molybdenum, when it is going to react with oxygen to give the molybdenum trioxide, so this one is insoluble in both water and insoluble in acid. That means it is not acting as a basic oxide because it is insoluble in water and insoluble in acid, but dissolved strongly in a base. That means when you dissolve it in a base, it gives a solution of molybdate ion. So that means if it is now dissolved in a base, that means it is acting as the acid. So, but generally, metallic elements are generally basic oxide, except some of the metals with high oxidation state where they can behave as the acidic oxide. Like for example, the molybdenum trioxide, it is now dissolvable in strong base. That means it is acting as an acidic oxide because it is dissolved in a base. So it is also insoluble in both water and acid. So if it is insoluble in acid, that means it is not a basic oxide. Because a basic oxide, when reactive with an acid, there should be a neutralization. So if it is insoluble in water and insoluble in acid, that means it is not a basic oxide, but this one behaves as an acidic oxide because it is dissolving into a strong base. So as a reaction, when you take this one plus a base, so you produce this ion and water. So we have also the amphoteric oxide. If you can check the periodic table, we have some diagonal element, diagonal region of the periodic table. So they are soluble in both acid and basic solution. That means you cannot classify them as acid or basic because they are soluble in both acid and basic. So consequently, we are calling them amphoteric oxide. That means amphoteric oxide, they can be soluble in both acid and base. So here, this one, they can dissolve in acid to produce salt and water, and they are dissolvable in a base to produce the soluble complex. So an example is, for example, the aluminum, which can be reacting with an acid to produce these ions, the aluminum, and the chlorine, that means is the salt. If you add them together, they form a salt. Then also we have this one, which can also react with the base. When they acting with the base, they give the soluble complex. You can see it is giving the aluminum hydroxide minus. So this is a soluble complex, and here they are forming a salt. Another example is chromium hydroxide. You can see it is reacting with acid to produce chromium 3+. So that means the bright violet solution of chromium 3+. It can also react with a base to produce chromium hydroxide. So which means this is a complex, a soluble complex, which is a green solution, which is for this complex, and this one for acid it will give the bright violet solution. So let's go to question 28. Question 28 is saying limestone deposit that form caves consist of primarily of calcium carbonate from the remains of living creatures. So that means we have calcium carbonate. This calcium carbonate is insoluble in water. Then they are asking, write a chemical equation describing when a limestone deposit are dissolved in infiltrated rainwater containing carbon dioxide. That means, although it is insoluble in water, it is soluble in rainwater containing the carbon dioxide. Then they are asking to write the chemical equation to describe this process where the calcium carbonate is going to react with the rainwater containing the carbon dioxide. They are also asking aluminum hydroxide is insoluble in water and is amphoteric. They are asking to write the chemical equation to describe the dissolution of aluminum hydroxide when an acid is added and when the base is added. So we have seen that the amphoteric compound, they can react both acid and the base. They are asking the two reactions when aluminum hydroxide reacts with acid and when it is reacting with a base. So another question, question 28 is saying copper hydroxide is insoluble in water and is also amphoteric. Write the chemical equation when an acid is added and when a base is added to the solution of copper hydroxide. So different reaction that we need to demonstrate. Just going to the question, let's start with the limestone. When you have the rainwater containing carbon dioxide, that means carbon dioxide is reacting with water to give the carbonic acid. And when this carbonic acid is going to react with the the calcium carbonate, then you produce the calcium and the 2 hydrogen carbonate. That means this one, it will be soluble in, because it is a base, it will be soluble in acid. So question number 2, they were sub-question number 2, they were asking aluminum hydroxide when it is reacting with an acid, it will give the salt, aluminum and chlorine, and when it is reacting with a base, it will give the complex, which is soluble, which is aluminum hydroxide. Then the sub-question number 3, the copper hydroxide, when it is reacting with acid, it will give the copper and iron and chlorine, that means it will give the salt. Then when it is reacting with a base, it is going to give the complex, which is soluble. So question 29, they are saying explain the effect of the pH on the solubility of sparingly soluble salt. The salt which has the very low solubility in water, then they are asking when you change the pH, when the acid is added, what will be the effect? So explain the effect of pH on the solubility of sparingly soluble salt. Let's see the answer. Actually, most of the anion which make the sparingly soluble salt, they are conjugate base of weak acid. Because when you have a strong acid, you produce, it is coupled to the weak conjugate base. And when you have weak acid, it is coupled with a strong conjugate base. So many anion which are composed with the sparingly soluble salt, that means the sparingly soluble salt, they contain the 2 ion. That means one it will be the cation, another will be an ion. So that anion is coming from the weak acid, which means if it is coming from the weak acid, it is a strong conjugate base. Conjugate base from weak acid are strong base and accept the proton in the solution. That means they will accept the proton in the solution. So you can see this one is coming from the carbonic acid, which is a weak acid. So that means it will produce a strong conjugate base because it is a weak acid. This one also, this one. So you can see they can attract a proton in the solution. That means when you add an acid will react with this ion, and their concentration is going to be decreased into the solution because they can accept a proton. That means when you add an acid, it can react with this ion in the solution. So for example, this one is a weak acid, so it will give strong conjugate base. So this one also is a weak acid, it will give the strong conjugate base. So this one comes from this one. Then you have this one is also a weak acid, it will produce conjugate base. So this one is a weak acid, it will produce strong conjugate base. So here also you have weak acid, strong conjugate base. So I'm showing you where this one they are coming from. So they are the conjugate base, and they are strong conjugate base because they are coming from this weak acid. And the anion, so in many sparingly soluble salt, the salt which has a very low solubility, sometimes they contain this for anion, and this anion behaves in solution, they behave as the strong base, the conjugate strong base. Even this hydroxide is coming from the water, which is weak acid, strong conjugate base. So what happens if you add an acid? When an acid is added to a solution containing this ion, there's an ion, that means they react with the acid reactive with these anions, then the solubility is going to be increased because the acid will react with this anion, decreasing their concentration, therefore forcing the more salt to dissociate to provide this ion in the solution. So this anion behaves like a strong conjugate base. They will react with an acid, decreasing the concentration of this anion in the solution. That means it will cause a more salt molecule to dissolve until an equilibrium is reached. So we have here the magnesium, for example, hydroxide. When you add the H+, will react with this hydroxide, therefore decreasing the concentration of hydroxide and shifting the equilibrium to the right. So that means more magnesium hydroxide is going to be soluble to compare to again supply the OH. So when acid is added, so that is what will be produced. The acid reactive with the OH to produce water. That means the OH concentration is going to decrease, therefore causing the magnesium hydroxide to be soluble to supply remove the OH. So that means removing the hydroxide will shift the reaction to the right until the equilibrium is reached. This is also KF2. This is coming from HF. HF is a weak acid. So it's a conjugate base of weak acid. So that means it will behave as a strong base. Don't get confused. This HF is a weak acid, not a strong acid. When strong acid is added, then the KF solution, so that means the acid will react with F minus, so producing the HF. That means removing the F will cause the more KF to dissociate, or it will cause the equilibrium to shift to the right until the equilibrium is the reaction to shift to the right until the equilibrium is established. That means adding an acid will decrease the F minus, then therefore more KF2 will be soluble, then to supply again the F minus. So in contrast, so when there's salt, they are having the base which are coming from the strong acid. So that means adding an acid will not have any effect. So addition of an acid has little or no effect on the solubility of salt, whose anion, if an ion is coming from a strong acid, because an ion coming from strong acid is it will produce a conjugate. It will be a weak conjugate base. When you have strong acid, they are coupled with weak conjugate base, while a weak acid, they are coupled with strong conjugate base. So the anion coming from the strong acid, so there's an ion, you have the chloride, you have bromide and iodine. So that means when a salt is having it is sparingly soluble salt having this anion coming from strong acid. That means adding an acid will not have it will have a little or no effect to the solubility. So that is when you have strong acid, they produce weak conjugate base. Strong acid producing weak conjugate base. Strong acid produce weak conjugate base. So that when you add an acid, that means a little or no effect on the solubility will be produced when you have the anion coming from a strong acid. Let's go to question 30. Question 30 is saying the KSP of the solution of magnesium hydroxide is 1.8 times 10 power negative 11. By using calculation, show that the solubility will increase when a strong acid is added to this solution. Here they are asking to show by calculation that when you add an acid to the solution of magnesium hydroxide, so then the solubility will be increased. So we have seen that the reason why the solubility is going to be increased is because the hydroxide is coming from the weak acid, and then the weak acid produce a strong conjugate base. So the strong conjugate base react with the acid. Then if the strong conjugate base react with an acid, it will decrease the concentration of that anion, and then therefore forcing the equilibrium to shift to the reaction, therefore forcing the reaction to shift to the right until the new equilibrium is established. But here they are asking to show by calculation that when you have magnesium hydroxide with the KSP 1.8 times 10 power negative 11, they are asking to show by calculation that adding an acid will increase the solubility. So that means increase the solubility, that means increasing the KSP of the reaction. So when they are asking to show that, that means when you add an acid, we are going to calculate the new Ksp, and we show that the Ksp has been increased. Let's see. So when you have magnesium hydroxide, that means we have 2 hydroxide with this Ksp, and when you add an acid, the acid will react with hydroxide, removing the hydroxide, forcing more magnesium to dissociate, then increasing the solubility. But here they are asking to explain by using calculation. So here, when an acid is added to react with the hydroxide, forming water. So now, what is the K for this reaction? The K value for this reaction, because when you are going to calculate the overall reaction, we should be having the Ksp for this reaction and the K for this reaction, so that you can calculate the overall K, and you see that the overall K will increase, because increasing the K, that means increasing more solubility. So how do we get now to calculate the overall K? We should be having also the K for this reaction. So if you check, this is the reaction which is also the inverse reaction when water is going to decompose. So the decomposition of water, that is giving the Kw. So this is the inverse of Kw. So because H2O gives OH plus H, then we get Kw. So that means here, when we are going to get times 2, that is the Kw times 2. So that means when you have 2 water plus, which give 2 hydroxide plus 2H, is the same as the 2 times this one, then you have the Kw, which is equal to, this is 10 power negative 28, because you need to take this one times 2, because we have multiplied by 2 on both terms. But this is not the reaction that you are looking for. We are looking the K for this reaction. As you can see, this reaction is the inverse of this reaction. That means to get the K for this reaction, we need to invert this Kw. That means the 2OH plus 2H plus, which give 2 water, that will give the K, which is equal to 1 over 10 power negative 28. Then you get 10 power 28. So that means we need to do the inverse. So that means this reaction will have the K, which is equal to 10 power 28. So then, after getting the K for this reaction, and we have the Ksp for this reaction, then we can write the combined reaction. This is the first reaction with the Ksp, the second reaction is the K. Then we can do the reaction, the combined reaction. This one is the same as this one. We can cancel this one, the 2. Then we write the overall reaction. The overall reaction is this one. Then we have a new K, which will be equal to 1.8 times 10 power 17. So you can see that this one, this K, the new K, is far higher than this one. Here we have 10 power negative 11, and here we have plus 17. So you can see that adding an acid will increase the solubility considerably, because the K is also increased extremely. You can see, if you compare this K and this one, you can see that we have a very large K value when acid is added. That means the K value which is higher, the more the solubility. So let's go to question 31. Question 31 is saying, read oxalate, read iodide, and read sulfate are all rather insoluble. They are insoluble. What effect does adding a strong acid have on the relative solubilities? Given the pKa for this one and the pKa for this one. So if you check there, we have this one, this one, this one. So now to know where the effect when you are adding an acid, so you need to check this oxalate. This is coming from the oxalic acid, which is a weak acid. That means this one will be a strong conjugate base, because we need to check how this one they react with who they added the acid. So this one is a strong conjugate base. It will react with acid very easily, because it is a strong conjugate base. But this one, because it is iodine, it is coming from a strong acid, and this one, a strong acid produce weak conjugate base. So this one is having a very low reaction with an acid. That means this one will have a little or no effect. But what about this one? This one is coming from the SO4, so that which means it is having the 1.99 as the Ka, the pKa. That means the more the pKa you have, the lesser. If you have the more what is the pKa? When you have a high pKa, the more you have the pKa was given here, the pKa, that means here also it was given. That means the more pKa, you have also if you have the more pKa, like for example this one is having the high pKa. You can see here it is having the high pKa. So that means you can compare with this one. This one is having the low pKa. What does it mean? So this means that this one with the high pKa, this one is the one which has which will produce a very strong conjugate base as compared to this one which is having the low pKa. We can also compare the pKa. So if you are comparing them, then you can have we have also the number II, which of the following is insoluble salt will be substantially more soluble in 1 molar the nitric acid than in pure water. So we have the silver and this one, and see here also they're asking which one will be soluble, which of the following insoluble salt will be substantially more soluble in acid. So here we have also the acid. That means this one and this one, they will have an effect. And what about this one? This one is coming from a strong acid, and it will be a weak conjugate base. So that means this one and this one, they are the one which will be more soluble in this one. So this one also it will have no effect or retro no effect because it is coming from a strong acid. So let's see their answers. We have the I. So when you have the addition of strong acid, they will have the greatest effect on the solubility of salts that contain a conjugate base of weak acid as the cation. So then this one, I told you that this one is a weak conjugate base from strong acid. So adding a strong acid to a saturated solution, this one, the greater effect is solubility. So here also, the higher the pK, the higher is the acid, the weaker is the acid. So that means this one is more weak acid as compared to this one. So because we have if you have the higher the pK, the weaker the acid. That means this one will have a very strong conjugate base because it is a weak acid as compared to this one. So that means the oxalate ion is a more strong conjugate base as compared to sulfate ion. So that means then the effect of adding the strong acid will be more on the red oxalate as compared to the red sulfate. So then we can go to II. So that means